Hello, welcome to this tutorial where I'm going to be showing you how to build a voice AI chat assistant, or in fact, I'm also going to be showing you how to add voice chat experiences to your AI applications, and we'll be taking a look at it in this video. I have this demo called AI Voice Assistant, and you may have seen this already online, but today I'm going to be showing you how it was all put together, all of the bits and pieces. And the beauty of it is you can take out the pieces you need to reuse in other projects you might want to integrate this with. Because in fact, interestingly, I was building this to create a spam caller through bot, because I always get spam calls and I want to keep them locked in a fruitless conversation for as long as possible, and it just makes sense building that with AI. So I'm going to be showing you how this is put together, how you can have real-time conversations, and all of the pieces that needs to come together to make this work. And then you can pick and choose which you want to use for your project, and in fact you can deploy the entire thing to your Cloudflare account for free. I'm going to show you how to do that, but first let me go into the demo and show you how this works, and then we'll take a look at the technical bits of it. So I have the application opened here. It's on the domain talktoai.conflare.workers.dev, and if this is your first time accessing the application, you'd want to give it permission to access your microphone so you can have that real-time conversation with the AI model. That makes sense. So I already have that done, so I don't think I'm going to get that prompt. What I'm going to do is click on the start conversation button, and then I'll start a real-time conversation with my AI agent, or actually my large language model. So let's start the conversation. Hello.
Hello. How can I assist you?
Let's play a game of two truths and one lie.
I'll start by telling you 3 statements, 2 of which are true and 1 of which is a lie. You have to guess which one is the lie. Here are my 3 statements. 1. The shortest war in history was between Britain and Zanzibar on August 27, 1896, and lasted only 38 minutes. 2. The longest word in the English language, according to the Oxford English Dictionary, is... The longest word in the English language, according to the Oxford English Dictionary, is pneumogen a lung disease caused by inhaling very fine particles of silica. 3. The Great Wall of China is visible from space. Can you guess which one is the...
It's the last one.
The Great Wall of China is not visible from space, despite its reputation as being the longest man-made structure in the world. It's a common myth that's been debunked by astronauts and satellite images. The other 2 statements are true. The Anglo-Zanzibar War was indeed the shortest war in history, and pneumogen is a real word that's often cited as the longest English word. Well done! Now it's your turn. You can give me 3 statements, 2 true and 1 false, and I'll try to guess which one is the...
Thanks, now that's a fun game to play.
I'm glad you enjoyed it. True, false, or lie, or 2 truths and a lie is a great game for sparking interesting conversations and learning new things. If you want to play again or try a different game, just let me.
All right, so we'll stop the conversation there. You get the idea. We can have real-time conversations with the AI model, and it's actually quite fast. You can see I'm able to speak into the mic, and it's able to get my response audio, and also you can see the transcription of what I said is displayed on the screen. And the AI is also able to respond like quite quickly, and we can also see the transcription of what is being said on the speakers on the chat, so you can read that as well. So let's take a look at how this is built. And before that, I actually have a link, a couple links at the bottom to the technology that was used to put this together. It's Cloudflare Workers AI. Please give that a try. Go check that out. And also here is a link to the source code of the application. It's all right here on GitHub. Don't forget to leave a star, and you can like take a look at this repository, see how it's built. We'll be doing some of that in that video, in this video I mean to say. And you can click on this button to get it deployed to your Cloudflare account for free. So that's really cool. All right, so what we'll be doing in this video is I'm going to show you how this works, how it was all put together, the technical bits. We'll start by looking at the front-end workflow. That's for getting your voice and sending it off. Then we'll take a look at the back-end workflow that does all of the transcription and the inference. And lastly, I'll wrap up by talking about how I plan to use the bits and pieces from this project in a next project I'm working on. So you want to stay tuned to see that. My name is Confident and I am a developer advocate at Cloudflare. Without any delay, let's get started. So for us to get started, I'm going to go over the broad architecture structure of this application, and you can see it right here in the GitHub repository. So under the how it works section, there is a diagram over here that explains literally how it works, and this diagram puts everything together out nicely. So when you give this application access to your microphone, it's able to collect the speech you are speaking from your microphone into the app, and the app runs a really lightweight voice activity detection model. Let's see if I can make this bigger so you're able to see it better. Okay, yeah, this is better. The application runs a lightweight voice activity detector, and that helps it to figure out when you are speaking and when you're not speaking. So it's able to capture speech when you're speaking or when your microphone is active, like actively collecting sounds. But if nothing is being said, it doesn't capture anything. And the captured speech, the chunk of captured audio, is then sent over to a Cloudflare worker that has a durable object. And this is going to be happening over WebRTC because we're building a real-time voice chat application, so it has to be WebSockets. So that voice audio is sent over to a durable object, and the durable object starts the workflow in quotes. What happens in a durable object is it receives that audio chunk and sends it to a speech to text model, because what you've said is audio and we need to perform inference on that audio. We need to convert that audio input into text because large language models typically only support text input. So we send that to a speech to text model to convert that. In this case, we're using OpenAI's Whisper model. And when we get that text back from the model, we send it to our LLM of choice. In this case, we're using Llama 3.1. Also, we'll see that in the code when we go take a look at it. But we're sending this to Meta's Llama LLM, and that does the inference. To figure out what you said and to generate a response. Then the response from Llama is then sent to a text-to-speech model. For this particular example, we are using MeloTTS. And the beauty of all of what we've done, when we take a look at the code, you see that it's really easy to swap out models for whichever you prefer without having to like change a lot of code or update the front end. And that's actually really cool. So the text-to-speech model converts the response from the LLM to speech, and you get the base 64 audio sent through the durable object back to the front end using WebSocket, and the front end takes that base 64 audio and converts it back into sound, like converts it back into wave and plays it in the browser so you can hear the response from the model. So this is a high level of how all of it was put together. And I think something cool about this architecture is that all of the heavy lifting is happening off device. It's not happening on the user's device, which means that any user with any device that can access the internet can benefit from this voice AI interaction, because the heavy lifting, the inference, the speech to text, the text to speech is happening off device. The only thing the actual device needs to worry about is capturing the user's speech and playing the response sound from the AI, which is pretty lightweight. We're also using WebSocket for real-time communication. That's awesome, and it's actually quite modular. As you see in the code, we'll be able to swap out any component we need to and like break this apart to use somewhere else. Remember, I said I'm going to be using this in my next project. So let's start by looking at the code, so I show you how the flow is put together, and you can actually take this and use this in your project. I'm going to open up my text editor. All right, and this is the front end file. This is a JavaScript application on the front end, of course. This is the front end file, and we have two main functions on the front end. The front end has separated the UI, so this is the actual application logic that you need to worry about. You don't have to worry about like UI stuff, the way the front end is structured, and you see that on the GitHub project as well. So the first part or function here is the one that sets up the WebSocket connection, because we need to connect to the backend, and all of this is just WebSocket housekeeping. But most importantly, what you want to take a look at is the onMessage event handler. That is because we're going to be receiving the transcription of our own speech, and we need to get that displayed on the UI. And you can see we have a line that does that. So when we receive a text data, we want to display that on the UI, and that's the user's speech. But when we receive an audio data, we not only want to display it on the UI, we also want to play it. You have this queue sound function that queues the responses from the AI and plays them as they come. So you get the sound played in order, and that helps to reduce latency because the sounds are processed as they come and they're played immediately. So that's actually quite cool. And this is all still WebSocket stuff. So on error, on close, that's the WebSocket stuff. And you have the function to actually like get the text displayed on the UI. Anyway, so the other interesting part in this front-end code is the voice activity detection system. And this function does the initialization of the voice activity detection system. There's a note here saying Firefox doesn't work, and that's because Firefox right now has a bug that prevents it from syncing audio from the user's microphone and the audio context if the sample rate is different. So that's a bug in Firefox. It's going to be resolved at some point, but this doesn't work in Firefox, and you get a note here if you try to open up the application in Firefox. All right, so we need to create a couple of functions to get the audio buffer sent to the WebSocket. So this is one of them. This is the onAudio buffer. When we receive an audio buffer or a chunk of audio representing a user's speech, we want to send that to the WebSocket connection, and that's what this function does. When we receive a status message from the voice activity detection system, like listening, speaking, user not speaking, we also want to show that on the UI, and here's where we go to get that those two functions sent off to the voice activity detection system, and then like it's able to get the speech and chunk it. If you want to see more of the voice activity detection system, it's going to be right here in vad/index.js. This does all of the microphone access, so to pick the user's microphone using the where is that part of the code, using the get user media, chunking that audio, resampling it, and converting it into an audio buffer. This does all of that processing, and you can see more information about it here. Okay, so let's close that file. When you do get an audio buffer, which represents a user speech, this gets sent to the backend. So through WebSockets, the buffer is sent to the backend. Let's move over to seeing what happens at the backend now. So on the backend, that's going to be in the index.ts file. What we're doing here is a couple of things. Because it's a WebSocket server and we need a durable object to set that up, we're doing some like housekeeping to make sure we are upgrading the user's connection to WebSocket and then sending that information to the durable object. If you don't know about what durable objects are, we made a video to the top corner here, so click on that video so you can go learn more about durable objects and using them to build real-time experiences with WebSocket. But anyway, this entry point is a Cloudflare worker that instantiates a durable object and then sends the user's connection to that durable object. So the connection is upgraded to a WebSocket and that gets sent to the durable object. And this is what the durable object looks like. So let's close that up. This is what the durable object looks like. It has a fetch method. This is the durable object. This is the durable object class. It has a fetch method which receives the user's connection that sets up a WebSocket pair between the durable object itself and the browser. That's the user's browser. And yeah, that's all like WebSocket stuff. This is the most interesting bit of it, the message handling bit. So we have a couple types of message. If the message type is a string, which means it's a command, we run this bit, and the only command we support right now is like clearing the chat history, which deletes the message history, as you can see here. But every other information that is going to be sent to this durable object as a message is going to be the audio buffer. Remember, over here on the on audio buffer, when we receive an audio buffer from the voice activity detection system, we send that array buffer to the backend. The backend receives that array buffer, so it receives the array buffer and starts to do a couple of interesting things. The first thing it's doing here is it's converting that audio buffer to text. It gets the audio buffer and tries to convert it to text using the speech to text model. So when we receive the array buffer, which is an audio buffer, we convert it to a unit 8 array, and then we run inference on OpenAI's Whisper model to get that text, to get that speech converted into text. And then we get a text response, which we print into the console, and that's all good. The other thing we need to do is we need to get that text transcript displayed on the UI. So we do a quick send of the user's text transcript to the UI so it can be displayed on the UI, and then we push the user's text into the message history, which is saved in memory. Then the next thing we do here is, now that we've been able to capture the user's speech and we've converted it into text, we want to do something with that speech. We want to run an inference. And in this case, we are using Llama 4 actually. I thought this was Llama 3.1. We're actually using Llama 4, the latest and greatest model from OpenAI. From Meta, I mean to say. So we're using Llama 4 to run the inference, and we're also passing the message history so that it has context of the conversation we have had so far. And that returns a result. As you can see, it returns a result, and the result is going to be a stream of text. So the reason we are returning a stream, or we want a stream in this case, is if we wait for the model to generate the full response, that is going to be so slow because it's going to take a couple seconds, and that's going to be noticeable. And you also want to have in mind that we're going to take that full chunk of text and we have to convert all that full chunk of text into audio, and that's going to take a long time. So it's just going to add so much delay to the entire process. So what we're doing is we're receiving a stream of results, like we're receiving a stream of words, and we're using this buffer to text helper function to help us figure out when the stream of words form a sentence. So we are processing on a sentence by sentence batch, and you can see that on the UI that the UI is able to work on sentences. So we're buffering the words streamed into sentences, and what we're doing for each sentence is that we're adding the sentence to the chat history, and more importantly, we are taking each sentence and we are doing the audio processing. So for each sentence, we do the speech to text audio processing to convert the sentence to speech, and then we send that sentence to the front end so that it can be spoken out. The response we're getting here is a base64 audio. So we're getting the base64 audio of each sentence and we're sending it to the front end so it can be played. And this is the part that does exactly that. The other thing here is just like WebSocket housekeeping, and that's the most interesting thing happening here. So moving back to the front end, when we receive an audio from the back end, we go to the WebSocket audio case. So we've gotten a basis for audio now from the front end. What we want to do is we want to display it on the UI. So you see the transcription on the UI. Then we want to create a queue or add it to a queue of audio sounds to be played. And if we take a look at this queue sounds function, so that's going to be in utils.js. What it does essentially is that it processes each sentence audio as they come, and we're doing quite a lot of things to get that processed so you're able to hear it. So the first thing happening here is that we're receiving a base64 sound. We want to convert that to an array buffer. Then we get the array buffer and convert it to an audio buffer. Finally, we can get it played and you get to hear the sound. So we're doing a couple of data transformation to get that played, and the end result is what you saw initially. We have this really cool application. Let me switch to the app. So we have this really cool application that is able to we're able to have a conversation with, and that's quite nice. So let's start another conversation. Let's play a game of Would You Rather.
I'm not familiar with a game called Buddha. Could you please provide more context or information about the game? I'd be happy to learn and play with.
Let's play a game of Would You Rather.
I think you might be having a bit of fun with me. There is no such game as Woody Rada or Buddha Rada that I'm aware of. It seems like you might be making up a game name.
Yeah,
If you'd like,
I meant
we can try
a
playing
game
a different
of
game or
Would
having
You
a
Rather.
conversation. I'd love to play a game of Would You Rather with you. In this game, I'll give you 2 options, and you have to choose which one you'd prefer. The catch is, you can't say neither. You have to choose one of the options. Here's your first question. Would you rather have a private island with a luxurious villa and unlimited resources, but be completely cut off from the rest of the world with no internet or phone signal? Or be able to travel anywhere in the world for free, but never be able to stay in one place for more than a week? Which one would you?
I think the last one. I would like to travel the world.
Traveling the world and experiencing new cultures, meeting new people, and trying new things can be incredibly enriching. Here's another question. Would you rather be able to speak any language fluently or be able to play any musical instrument?
Play any musical instruments for sure.
Being able to play any musical instrument would open up so many creative possibilities. Imagine being able to pick up any instrument and play it like a pro. Here's another.
Okay, so let's stop the conversation there. So you get an idea of how the model is able to receive the audio because we have a voice activity detection system running in the client, getting the audio chunks, sending it over WebSockets to the durable object, and then the durable object performing the speech to text by running a speech to text model, the inference on an LLM, and finally converting the text back into speech that is sent back to the client to be queued as audio and transformed into actual audio that is played to the user for them to hear. So that's an overview of how all of this comes together to build this experience. And as you can see, I tried to keep it modular so you can pick and choose the parts you need for the project you're working on. Anyway, the entire source code is here on GitHub, and you can go take a look at it and play around with it and build something awesome on top of it. So before going, I'm going to talk briefly about what I'm going to be building next. I plan to use this project inside of an AI agent. So right now, the agent interfaces we have is like all through chat. I want to be able to talk to my agent and get it to do stuff. And I have a couple smart devices in my home. So I'm going to hook it up to an MCP server that has access to tools to control stuff in my home and just have a conversation like, hey, can you turn on the light? And get it to turn on the light, or say, hey, can you change the color of the light, and get it to change the color of the lights. So that would be really awesome to see, and that's what I'm going to be building next. I'm still working on my spam caller throw bots, and I'm going to update you guys on the progress with this project. And yeah, that's it. I think this is really awesome. I know you guys will have a lot of fun with it, so let me know in the comment section what you will be building with this, and I'd love to hear from you. Thank you. See you in the next video. Don't forget to get subscribed so you don't see our future videos, and I'll catch you in the next one. Take care. Bye.